Chirality is the Greek word for handedness. It's the property of any two things to be mirror images of one another. For instance, your hands are pretty chiral, and that's why you cannot wear a right-handed glove in your left hand and vice versa. Just like hands, molecules also exhibit this property. They can have the same bonds and the same atoms, but still interact in completely different ways based on their spatial orientation. Two molecules that are mirror images of one another are known as enantiomers. Here's where it gets interesting though. When we look at life on Earth, things start to get seriously left-handed. All the molecular building blocks of life are oriented with the left chirality. Not only that, they cannot be replaced with their right-handed counterparts. You see, although these enantiomers are physically and chemically the same molecule, but their effects on our bodies are very different. This is because our bodies are also chiral, and so going back to the same glove analogy, replacing our body's left enantiomers with the right ones is the same as trying to wear right-handed gloves in your left hand. It just won't work. For some unknown reason a few billion years ago, evolution took the left-handed route, and it just never looked back. One may wonder today what a right chirality-based life would look like, or if it would even allow for life to survive for so long. If you take a molecule of limonene, the main ingredient in lemon extract, and use it as a blueprint to generate its right-handed enantiomer, you would create something which tastes like black licorice. This experiment goes on to show that our taste buds are also chiral and can distinguish between enantiomers. On a lighter note, chirality is also the reason why I look moderately good in the mirror, but ugly as hell in photographs. Oh, and did I mention the main ingredient in Vicks Vapor Rub is a left-handed enantiomer of methamphetamine. So, do what you will with that knowledge. If you haven't been living under a rock, you must have heard of the phrase, mitochondria is the powerhouse of the cell. Mitochondria is an organelle that is present in each and every cell of your body. It uses a series of chemical reactions to convert glucose into energy in the form of ATP. What most people don't realize though is that mitochondria was not always the part of human cells. In fact, it was not part of any multicellular cell. The endosymbiotic theory tells us that what we know today as mitochondria originated as a completely separate single-celled bacterium. So the story goes that some 2 billion years ago, our ancestral cells swallowed this bacterium and didn't digest it properly. This undigested cell continued to live inside the host cell, eating stuff and making energy. Over time, the creature living inside divided and replicated, and so did the cell that swallowed it. All multicellular forms of life can trace their ancestry back to this one event. As time went on, the mitochondria lost a lot of its genes that it needed to survive on its own, while the nucleus of the host cell gained them. The mitochondria is still technically a different creature with part of its own genome still intact. I just find it really hard to digest how an extra hungry cell some 2 billion years ago decided to join forces with a rival cell. They eventually got to know each other and are now running a multi-billion cell industry that is our body. Before Einstein, people thought about time like an absolute entity. Like there must exist a kind of universal clock in the palace of God somewhere that always shows the correct time. A kind of universal time. This idea of a universal time was neat and easy to understand. In fact, most people today who are not familiar with relativity would think this idea to be true. But Einstein had a problem with this idea. He showed that there is no universal clock and no universal time. Everything is relative, he said. You are not poor, it's all relative. You're not ugly, it's all relative. Twilight does not suck, it's all relative. You're not a guy or a girl, it's all just relative. And this principle applies to time as well. Two people in different frames of reference will have their clocks moving at different speeds. For example, let's imagine that I'm sitting on a bench thinking about why people won't subscribe to my channel. If I had a watch on, it would show time passing at a normal speed. Let's call it t. Einstein argued that this t was dependent on who was observing the watch. Since me and the watch are both at rest, or to sound more pretentious, since we are both in the same frame of reference, I can think that t is the natural speed of time. But I would be wrong. If I take my watch off and place it on the bench and start running in any direction, my frame of reference would change, and if I observe the watch now, which is moving away from me every second, I would find that the clock is moving slower than t. However, the important thing to note here is that in the frame of reference of the watch, time is still moving at its natural pace. And if while running I check the clock on my phone, I would also find that time for me is moving at its natural speed. A lot of people tend to misunderstand this one detail, that nobody actually experiences time slowing down. You will always see your own clock ticking away at 60 seconds per minute. After all, from your frame of reference, you aren't moving at all. It's everyone else who is moving backwards. Think about the Spider-Man meme, but all the three Spider-Men are in different frames of reference, and so all three of them think that their own clock is showing the correct time. But when they look at each other's clocks, they will find that time is moving slower than their own clock. And they would all, in fact, be right.
99%
You can never really
of
touch
an atom
anything,
is
but
just
only feel the
empty
repulsion
space.
of the outer electrons of the thing that you're trying to. You may have heard or read these statements in passing multiple times before, either in a science book or on YouTube or as an obscure fact on the internet. But even though these statements are sometimes tossed around like random trivia, the science behind them is really far from trivial. The issue with statements like these is that they make the assumption that atoms and their subatomic particles have well-defined positions and boundaries, like in the Rutherford model. So computing the empty space in an atom becomes a very easy task. Just sum the volumes of the protons and the electrons and subtract it from the volume of the outermost electron shell. And sure enough, you will get 99% empty space. Except, atoms are not miniature solar systems as proposed by Rutherford. They operate much more like waves at quantum scales. The position of an electron is always in a superposition of states until it is measured. This is known as the Copenhagen Interpretation. In simple terms, electrons are spread around the atom like a cloud, and only once we interact with this electron cloud does it collapse into a particle with a definite location. The thing to note here is that before we interact with the electron cloud, its position was not well defined. It was spread around all over the place like a wave. So in a strange setup like this, how do you go about calculating the volume of the atom? How do you determine the size of the electron cloud, since electrons don't have a finite position? There's always a finite probability of finding the electron anywhere in space. Albeit a small one, but still it cannot be discounted. And what does touching something really mean at the quantum scale where nothing has any clearly defined boundaries? I think the best we can do is to probably just refrain ourselves from burdening this subatomic world with notions of our own macroscopic views. Or in the words of Professor David Mervyn,